All right, my loves, I'm so excited to talk about geometric sequences with you. So, a geometric sequence is an ordered sequence of numbers um, where each term is multiplied by a common ratio. So we talked about arithmetic sequences before where we are adding or subtracting the same number every time. But now, and that could be modeled by a linear function, but now we're going to talk about a type of sequence where each term is multiplied or divided by the same number. So since these sequences are multiplied by a common ratio, we can model them with an exponential function. All right, so let's look at what's known here as this explicit form. So a sub n, that tells us the value of the nth term, where n here is just an integer or a natural number, really telling us what number in place we are. So, like, if you think about children, right, there's a lot of kids in my family, right? First, second, third, fourth, fifth, so on. All right, I'm number one, firstborn, right? So I'd be n and it equals one. All right, first term. So the value of the first term is this guy here, a sub 1. And so really we should just be able to say first term, this is the nth term, but I like to put in the word value to help remind students that the a sub n or a sub 1 is not telling us the place, like first place, second place, third place in line. That's what n itself is for, but it's telling us who is there, right? Who, where the value of that term. All right, and it's much like the starting amount or the y-intercept when we were talking about linear models. All right, R, that's our common ratio. It's the thing we're multiplying by over and over and over and over again, right? It's the base of our exponential. And n is our term number, like I've said, right? It's telling you first spot, second spot, third spot, so on. All right, so I'm going to show you 3 ways that you might encounter these. I'm going to give you a word problem, which is not always how we talk about sequences. Usually you'll see it like example 2 or example 3, but I think it helps us wrap our head around what's going on here. Then we'll look at an example where it's just kind of a boring sequence. I'm literally just giving you a list of numbers and we're going to talk about it. And then we're going to look at a visual, which is my favorite way to talk about sequences because I think students just are able to piece together what's going on here so much better. All right, so we're going to talk about puppies because who doesn't love puppies? So we have a puppy named Calvin, and he is doubling in weight each month, okay? So his weight doubles every month. Oh, and I used the wrong color highlighter for that. So this is our rate that's taking place, doubling every month, okay? If he weighs 3 pounds now at the start, how much is he going to weigh after n months? So we are going to write this explicit formula. So this is going to look like a sub n for his, a sub n is standing for his weight at n, after n months in time. That's going to be equal to 3, his starting weight, times 2, because he's doubling in size, raised to the n minus 1. And what's really amazing about these explicit formulas is that if I want to know after 27 months how much is Cal going to weigh, I could plug that number in and figure it out. Now let's talk about an explicit formula for this, what I call the boring sequence here. So we have to figure out two pieces of information, right? What was the first term? What was a sub 1? And then how's this thing changing, right? So let's see. A sub 1 is going to be that starting number in the sequence, in this case, -7. But then we need to think about how is it changing from -7 to 14, from 14 to -28, from -28 to +56. So what's happening here is we are multiplying by -2. So big giveaway that it's negative is my rate here is negative, or my common ratio is negative, is that I'm alternating signs on my terms, right? Negative, positive, negative, positive, negative, positive. So that lets me know, right, if it is raised to a positive exponent, then it's just going to be positive, and that's how I end up with a positive term, like 14 or 56. But if it's raised to an odd power, like 3, 5, 7, 9, that's when I'm going to end up negative. All right, so I ended up getting that a little bit wrong because the base is also negative, like just in terms of the equation itself. But what I said about evens producing a negative number, just in a general sense, odds produce, or a positive number and odds producing negative, that was correct. Sorry. Oh, the choice of being a chronically ill teacher. So we have a sub n is equal to -7, that starting amount, times -2, that's being raised to n minus 1. All right, so the figures below here depict a visual pattern that can be modeled by a geometric sequence. Write an explicit formula to model the sequence. So we're talking about calculators, obviously. It's a great thing to talk about. So we need to know how many are in each figure. So we've got 2, then we've got 6, and then we have 18. So I know 2 represents my starting amount. And then how is it changing from figure to figure, right? From 2 to 6, from 6 to 18, it's being multiplied by 3. So my explicit formula is going to look like a sub n is equal to 2 times 3 to n minus 1 power. Awesome. All right, next, we are going to write an explicit formula to model the sequence. Again, it's a number sequence, not always the most fun. So go ahead and actually pause and figure it out, and then see if you can determine for me a sub 6 as well, or the value of the 6th term. All right, so you may have discovered that a sub n is equal to 0.5, right? That was our first term. And it's being multiplied by -3 to the n minus 1 power. All right, now to determine a sub 6, what we do is we plug 6 into our function. So it's be 6 minus 1 to the 5th power. And so I like to use Desmos or TI rather than my phone calculator For problems like these, especially involving all of this multiplication and exponents and negatives, I think the phone calendars really just can't hold a candle. All right, so when you plug that in, hopefully you got out negative 121.5. All right, so geometric sequences can also be modeled by what's known as a recursive form. So recursive form, you'll have to know the previous term. So rather than it being a function of the term number where I could just plug in the term number and get out whatever I had before, I'm going to need to know the previous term for this recursive. So a lot of the main players here are the same. So a sub n still, right, the nth, this represents the nth term. R still represents the common ratio. But a sub n minus 1, that is the previous term. So if I wanted to find the 6th term, I'd have to have the 5th term to be able to do that. So this is still R there. All right, so a baker is tripling her dough each batch. Okay, so that is telling me that my rate is multiplied by 3. If she starts with 3/4 of a cup, how much will she have in the 4th batch? So I have to know, right? If you think about the recursive form, I have to know the previous term. So for example, if I know that I have 3/4 as my first term, all I would do is multiply that by 3. And instead of n, I'm going to say that this is my second term. So a sub 2 is going to be 3/4 times 3. Okay. And I'm going to start converting these to decimals because I think it'll just be easier. Yeah. So if I have 9/4, right? I don't know about you. I don't have a measuring cup that says 9/4 at home. So, mixed numbers would actually be really good. That's probably what I would probably do if I was actually baking, but I don't use mixed numbers a whole lot in class. Sorry, tangent. All right, so if I were to start listing these, that's term 2, term 3, term 4. So we know we had 3/4 to start. Then I'm going to have 2.25. And then I just have to keep going in this manner, right? Keep multiplying by 3. So then I'll have 6.75, right? Would be the 27/4. And then multiply by 3 again. That's going to be 1/4 or 20.25 cups. And that's what she would need. 20.25, right? That's 20 and a fourth if you want to think of it as a mixed number. All right, but again, I'm too seriously about this, the application. All right, so let's write our recursive formula to model the sequence. Again, it's just one of those boring things going on here. So if I have some so a sub 1, I think that's important to know, is 100. Okay. But for everything else, a sub n is going to be equal to a sub n minus 1 times 1/10. And how I figured that out was I noticed I was dividing by 10 each time. All right. So again, we have figures that we're going to look at here. And of course, if we did calculus before, we're going to do coffee mugs now because this is coffee and calculus after all. So we've got 6 cups here and then 3 cups here. And then this is 1.5 cups here. And I did cut this icon in half, precisely in half. And if you're like, that doesn't really look like it's precisely in half, remember that this handle takes up part of the width. Anywho, again, taking way too much time. So what's going on here, right, is that these were being multiplied by 1/2, aka divided by 2. So of course a sub 1 was 6, and then we need to know a sub n for all the other guys are going to be a sub n minus 1 times that 1/2. And there you have it, folks, geometric sequences.